Bismillahirrahmanirrahim. Dear student, Assalamu alaikum. Welcome once again. As usual, I would like to start from the summary of the previous lecture, and I am sure that you have captured the fundamental assumptions of the classical linear regression model. Classical linear regression model is extremely and intensively used in all the researches, in the all kind of research and discipline. So I would like to give you a brief sketch of the previous discussion. First of all, there were 10 assumptions about the classical linear regression model. The first assumption, the basic assumption, was very simple: the model should be in linear. I think it will be over repetition if I give a detail of these assumptions. I would like to only go through these of the some of the major assumptions. The second was that there should be the residual sum of the error term should be equal to 0. The third was one that there should be fixed values of the independent variable, that are the x's. So the next one was there should be homoscedasticity. What this means, that the variance of the residual term should be a constant number. Similarly, we came across the assumption that there should be no autocorrelation between the residual term. Justification, what's its consequences, we will be discussing it in detail in our next coming discussion. The other assumption about this was the number of observation should be greater than the number of parameters to be estimated. And similarly, we also assumed that the classical linear regression model also assumed that there should be no perfect multicollinearity between the independent variable. After this, we immediately went towards, before going further, I would like to give that no assumption is less important as compared to others. All had its importance in the classical linear regression model, and if we will be ignoring any one of the assumption, we will be penalized. We will be penalized means our estimates, that are the coefficients of the regression, that are the beta 1, that is the intercept, and beta 2 hat, that is the slope coefficient, they may be suffer some of the fundamental drawbacks. So after this, we went towards the precision of this. Was a very interesting thing, that out of a same population there are number of the sample. So a person with different sample will come out with the different values of the estimators. So how to choose the best value of the estimator? We need the precision of the estimators, and for this we went towards the standard error. Standard error is nothing but it is the standard deviation of the distribution of the parameter. Completing this, we went towards the covariance of the beta 1 hat and the beta 2 hat, and we found that at one side the values of the beta 1 and the beta 2 hat changes from sample to sample, but within the same sample there may be interdependence of one parameter on the other. This was called the covariation, and we found the formula of this, and we found that the values, the symbol of the x bar is extremely important. In other words, you can say the x bar symbol is the decisive element in that formula, because the variance of the beta 2 hat will become positive, because the variance of any of the parameter is a positive number. So what today we are going to cover, we will see first, and then we will start our discussion according to this. First of all, we will see what is the Gauss-Markov theorem. What is a fundamental and very interesting thing that will help us in that what are the characteristics of the parameters, OLS parameters, when they are based on the fundamental assumption of the classical linear regression model. And you know what are the assumptions. After this, we will discuss the coefficient of determination. That is also another name of the measure of goodness of fit. every researcher at the end of his research completion wants to know that how much his model was fit according to the theory. So there should be some measure, and this measure is called the coefficient of determination. After this, we will see another very practical and very important technique that is called the Monte-Carlo Experiment. So we will go step by steps and we will see, and I will expect from you that you repeat this Monte-Carlo Experiment. It will benefit you on two sides. On one side, you will be aware of the statistical software EViews that I am going to introduce in a few lectures, and the other will be you will be crystal clear about the properties of the least square estimator, that are the estimates beta 1 hat and beta 2 hat. What are the properties? Gauss-Markov theorem gives us that what are the properties of these parameters, that are the beta 1 hat and the beta 2 hat. So what this is, first you should be crystal clear that these properties are only fulfilled when there is assumption, we take the assumption that we discussed previously. The first is what the Gauss-Markov theorem says. Given the assumption of classical linear regression model, look at this, it starts its definition with that given the assumption of the classical linear regression model, the least square estimators are below. A new term here is the below. So we should know what are the below parameters, what are the below estimate. We should know about this, and it is not the below color people, it are the below properties of the estimates. So what is this? An estimator now estimates the sample numerical values that are the beta 1 hat and beta 2 hat. If any of the estimate fulfill the following three conditions, we will say that the estimator is below. The first is linear. It is linear, that the parameter is a linear function of any random variable such as the y in the regression model. So if it is linearly related with the regression, you can say the dependent variable y, we will see that it is linear. So it is the first characteristic of its belowness. The second is it is unbiased. This is very important. Unbiased means it is neutral, and what this means, that is its average or expected value. Now go for another thing, that we are going to take the average value of beta 2 hat. Beta, we can also take the values of beta 1 hat. I am just concentrating on one of thing, that beta 2 hat. Beta 2 hat average value, what this says, that from different sample there will be different beta 2 hats. So if we take 10 sample, there will be 10 values of the beta 2 hat, and if we take the average of those 10 values, it should be equal to the true parameter, that is the beta 2 that is in the population. So if the expected value of, look at here, if the expected value of beta 2 hat, it becomes equal to beta 2, that is the true parameter, we will say that the estimate, our estimate is unbiased. The third characteristic it should fulfill is it has minimum variance. It has minimum variance. This is very important. Minimum variance means when we make its sampling distribution, you will say probability distribution, we will come to know that its spread should be minimum. It may have larger spread. If one person take 10 sample, he has the probability sampling of beta 2 hat, the other has also 10 sample, their probability may be a bit different. So what we are going to say, if he makes the beta 2 hat from some other method, then the probability distribution may be different. So it will help us to choose that which we are going to adopt. So what is the Gauss-Markov theorem in a very small sense? It is about the properties of the our estimates. It says that if the fundamental assumption of the classical linear regression model are fulfilled, our estimated parameters, or you can say our estimates, are below. What are below? They are linear, they are unbiased, and they are linear, unbiased estimator, and they have the minimum variance. And when they have the minimum variance, interestingly, they become efficient estimator. They are also called the efficient estimator. If we want to say a graphical representation of the GM means Gauss-Markov theorem, as we will assume something, and at the end we will be making, and it will help us that which parameter is below and which is not below. Suppose we take two different parameters. For example, let me come this what we are assuming. The distribution of beta 2 hat in repeated sample is symmetrical. We say that it's symmetrical means that it is normally distributed. Now this is beta 2. This is our assumption, supposition, that we assume that the sample distribution repeated sample, the distribution of beta 2 is symmetrical. One other thing we assume that beta 2 is unbiased. Unbiased, now you are aware that if we take the expected value of beta 2 hat, it is equal to the true value of the parameter, and its expected value is equal to the true parameter. Two assumptions we have made here about the parameter, about the estimates beta 2 hat. We are just concentrating on beta 2 hat. The similar things will apply on the beta 1 hat. So if we are going again for beta 1 hat, it will be, I think, the futile exercise, because the similar things is applicable to the beta 1. Take another parameter. This was about the one parameter. Say a person takes this assumption. We take that another person takes a counterpart of beta 2, and he calls it that it is beta 2 star. He says that there is a counterpart of beta 2 hat and it is a counterpart of beta 2 star. So what estimated from other than OLS. Beta 2 hat is estimated from OLS, ordinary least square method, and this is other than OLS. Any method, maximum likelihood maybe. So what this means, we further suppose this, that assume that beta 2 is unbiased. ये assumption भी वही है जो कि हमने बीटा 2 के बारे में, सिर्फ यहाँ पर एक डिफरेंस आ रहा है कि बीटा 2 के बारे में हम कह रहे हैं कि वो OLS से एस्टिमेट हो रहा है, एंड वी आर सपोजिंग दैट बीटा 2 स्टार इज बीइंग एस्टिमेटेड बाय सम अदर मेथड rather than the ordinary least square method. So what we are going to, the other assumption are the similar. Beta 2 hat is also unbiased. Beta 2 hat beta 2 star is also unbiased. Beta 2 has symmetrical sampling distribution. Same is that the beta 2 star has also a symmetrical distribution. And we further suppose that both parameters are linear. So it means the theory assumption about two things, beta 2 hat and beta 2 star, are the same. The first assumption is their distribution is symmetrical. The second is that both are the unbiased. The third is that the both are linear. The both parameters are linear. So now what we are going to do, we have two now values, beta 2 hat, beta 2 star. So which we have to choose? Which is the good one? Which is the best one? Come with me. I will show you the graphical representation. I would like to show you this on the other slides. First, look at this. If you look at this, before this, I make now the sample distribution of both beta 1 hat and beta 2 hat and beta 2 star. This is beta 2 hat, and this will be distribution of beta 2 star. And simply remember, this is estimated by other than OLS, and this is estimated by OLS. So what this means, suppose this is the distribution of beta 2 hat. It should be symmetrical, and I say that this is the distribution of beta 2 hat. And similarly, here at the beginning, what this means, that the expected value of beta 2 hat is equal to beta 2, that the true parameter, that we will show that this is the unbiased. Similarly, we are making here the distribution of beta 2 star. This will be also symmetrical in nature. Here beta 2 star now, and you know we estimated it from some other method, and it is also unbiased. Expected value of beta 2 star now is equal to true parameter beta 2. What this means, I make its distribution in such a way that this is more diffuse as compared to them. Now I combine both of these things, and I am sure you will immediately guess on your previous knowledge that which parameter is more appropriate than the other. Now I am combining the both distribution. This is now beta 2 hat and beta 2 star. So this is the distribution of beta 2 hat, and this is the distribution of that I have showed with the dotted line. This is the distribution of beta 2 star. Now look at this. This is beta 2 hat and this is beta 2 star distribution. Now if you see which has the more variance, and you will immediately guess that the beta 2 is widely spread as compared to the beta 2 hat. Beta 2 star distribution is more diffuse, you can say more diffuse, more spread as compared to beta 2 hat. So now you can decide that your good parameter is beta 2 hat. So the distribution of beta 2 star is more widespread around the mean value than the distribution of, look at here. This is the mean here, and you can see the beta 2 hat is not widely spread around the mean, but beta 2 star is more spread around the mean. In other words, the variance of beta 2 star is larger than the variance of beta 2 hat. It is correct. On the same knowledge we can say that what this means, that the variance of beta 2 hat, beta 2 star is greater than variance of beta 2 hat. Now one would choose the estimator with the smaller variance. You should choose the estimate that has smaller variance, because if they have smaller variance, it is converging towards mean, and it means it will be unbiased. Its true value, when you will take its expected value, it will represent the true value. In short, what one would choose the below estimator, best linear unbiased estimator, and you can say that this is the Gauss-Markov theorem. Theorem is remarkable in the sense that it makes no assumption about the error term. This is very important. Gauss-Markov theorem make no assumption about the error term. Before going to the further discussion, I would like to repeat this, that the Gauss-Markov theorem is only concerned about the properties of the estimates that are the least square estimate, and it has showed that under the certain assumption the least square estimates have the minimum variance. We have showed that if we measured some other parameter beta 2 star with other method rather than the OLS estimator, OLS method, then it has more widespread distribution. In other words, it has a higher variance. It means it is not comparable with the beta 2 hat, because beta 2 hat that was measured by the OLS, it has the minimum variance. Now we are going towards another you can say the numerical value, that is the coefficient of determination, R square. Do not confuse it with the R was the simple, that was the measure of correlation. It was a numerical value, the coefficient of correlation, that tells us what is the degree of association between the variable. This measure of goodness is, if you see that this is the R star, it means R square, it means it is a measure of goodness of fit. And if there is the regression analysis, if we will see here multiple regression analysis, only terminology change. We will use the capital R square. We are interested, we start the discussion of the coefficient of determination, that we are interested in finding how well the sample regression line fits the data. We are interested in here. Just let me say that if, for example, this is the data very near and this is the regression line, it fits more the data. And it is very near to the true population if we have selected the sample on some specific criteria. If all the points are on the line, it is perfect fit. I am going to just show you, but it is impossible. For example, if you see here, if all the points are here, this is X, this is Y, and if this is the line and all the points fall on the line, this is the best fit. Best fit. It is very easy, but it rares it is rare in the practical life. The next is, generally there will be some positive UI hat and some negative, because I said that it is a very rare chance that all the values are on the regression line. Definitely some values will be above, some values will be below. The values above will be called the plus UIs and the values below this will be negative UI. Now what is the coefficient of determination, to whom we will mention by small r square in two variable case and capital R square in multiple regression, is the summary measure. It tells us that how well the sample regression line fits the data. We need not to draw it, we need not to this. It is a numerical value that will tell us that how our data fits to the population. The R square is simply a numerical measure of this overlapping. So first of all, I would like to give, for example here, that if R square is, just let me see, I would like to give you that the Venn diagram or the Ballantine view of showing R square. For example, suppose this is the Y and this is the X. Now you can see both are independent. There is no overlapping. Do not afraid, I am not talking about the probability, but I am talking about how much variation in Y is explained by X. Here only we have assuming the bivariate regression model, so it means only I will be talking about 1X. So if you look at this diagram, I can say that this is the Ballantine view and this is the 1. You can say that the variation is Y is not explained by X. Even not a 1% variation is of the Y is explained by the independent variable, that is the X. So immediately you will guess that the R square is equal to 0. It means our model is purely fit, very poorly fit. Because the R square is 0, there is no relationship between the variable and our model. We have taken some of the independent variable that have no relationship with each other. Y is something else. You can suppose this is something from other population and the X from some other population. Now go further and I am going to show that this is Y and now just X is explaining some of its portion. Look at this. This is the X. Now if you see that X has become some potential variable and it has ability to explain the variation in Y, but the potential is very low, but we can say that there is something that can be explained by the X. So I can say that if this is the second diagram, here R square is only, I can say 5%, 0.05. I will be talking about that what is the range of this. So this is measured in percent. So what this is, that there is a very small variation in y that is explained. And now jumping towards the other one, look at this y, and you can see this is the x. This portion of y is being explained by x, and immediately suppose that it is equal to 80%. So what this means, now model is becoming better and better as compared to the first our Ballantine view. We came to know that the variation as y is now explained by x. So x has become a very important variable that has potential to explain this phenomena. And further go this, that happens rarely in life. So this is x is equal to y. Now all the variation in y is explained by x. So it happens rarely. It is just this thing that in this way the r will be equal to 1. So this is the measure of goodness of fit that will tell us that how much our model is fit to the data. So if what we want the more and more value of the r square. If it is very near towards 1, we will be saying our model is becoming more and more fit. So what this the other, if you come here, the sum of the various sum of squares. Sum of squares means the deviation from the mean, or you can say that this is the variation from the mean. I have just confined myself and I have abstracted a very important information from here. Otherwise there are very tough and complicated formulas. So what I am going to explain, I am going to explain the theory of regression, and we will see that what is the theory of regression. So first of all, there is, if you see here is a word that is total sum of square. Total sum of square, if you look at the formula, this is the deviation of the deviation of a yi values from their mean. So I will be plotting it on the diagram, and then we will be discussing that what is this thing. This TSS is a combination of two things. Now TSS means total sum of square. Total variation in y depends on two things: the variation explained by this regression plus the variation that is unexplained, that is the error term. So this is, if you look at here, this is the ESS. ESS means that explained sum of square, and if you see, this is the deviation from, this is the estimated value, and this is the y bar. So this is explained variation, and it is explained by nothing but only by the regression. And the last one is residual sum of square. So I am sure you are now aware of this: TSS, total sum of square, and ESS, explained sum of square, and RSS, residual sum of square. You can also call this unexplained. Unexplained. So it is equal to summation ui hat square. Summation ui hat square means that this is the unexplained proportion. So if you look at there, this is the TSS, this is the total sum of square, and it is equal to explained sum of square due to the regression plus residual sum of square. And how there is one of the formula, there are many other formulas, and I will suggest go through my recommended books, go even to another statistical books, and come with the formula of the R square, that is the coefficient of determination, or you can say the measure of goodness of fit. So this here is the formula for this. If you just write here, that I would like to write it here, that this is the RSS is equal to this is the TSS is equal to explained sum of square plus residual sum of square. Let me see, is there any explanation further? No. So this is if I divide both sides by TSS. So this is, I divide this one TSS, this will also divided by TSS, and this is also divided by TSS. This will become 1 is equal to ESS over TSS plus RSS over TSS. Now you can say the overall variation in the regression in the population is equal to 1, and its portion will be explained by the regression. This will be the explained sum of square, and definitely there are forces that we are unable to capture, and their effect will be residual sum of square. If you want to draw the formula from here, right, you can say that this is R is equal to, simply because it is explained sum of square divided by total sum of square. This is the formula here. Explained sum of square, and what is the value of explained sum of square? Yi hat minus y bar square divided by summation yi minus y bar square. And similarly, if you find that R is equal to total variation minus unexplained variation, that is residual sum of square divided by total sum of square. This is only a mathematical trick that can be, we can, if there are three values, total sum of square and the explained sum of square and the residual sum of square, if we have any of the two values, we can find the other value from here. So I would like to have discuss two properties. The first quality is it is not a non-negative number. It is non-negative number, although in some extreme cases that is some different kind of regression. In some extreme cases it becomes minus, but it is meaningless at there, because if it becomes minus, what does this mean? That the variation in the dependent variable is explained by minus 80%. It has no meaning. So it is non-negative number, and its range is very good. I would like to draw its range here. So it ranges between 0 and this is 1, and R square is equal to here is 0.5, 50%. So what this means, if you see here, the more and more you go towards 1, your model reaches R square of your model, the goodness of your fit reaches towards 1, your model is becoming more and more fit. Become happy and show, make boost of this, that you have a higher R square. But at the same time, I am giving you some caution that the R square is only very acceptable and very appreciable, its high value, when there is a time series data. When there is time series analysis, in time series analysis, we recommend that there should be higher R square. But in cross-sectional and panel data, even a lower value and smaller value of the coefficient of determination is accepted. So now just concentrate on your research, that if you have time series data, then try to get the higher value of this goodness of fit, and if you have not the time series data, then even a smaller, even less than the 40% variation is acceptable. Now I would like to draw these all residual of sum of square. In other words, I am just squeezing the whole discussion of the regression into this diagram. So you should be very keen in understanding this diagram, and I will not be skipping a minor step so that you could understand this, that what is the residual sum of square, what is the total sum of square, and what is the explained sum of square. So if I take here, this is x, this is y, and I suppose that this is your estimated regression function. This is y hat is equal to beta 1 hat plus beta 2 hat x. You can say this is I. Now I suppose that this is the y bar, this is the value of y bar definitely, and regression goes through the mean values, and I say that here is the x bar. And if I extend this value and I take here xi, I suppose that this is xi, and looking at this I would like to enlarge this, and this is y. So what this I say against this xi, there is a value of this is yi. The line is a bit you can say trend due to this electronic pen, and as there is no immediate recovery for this to erase this, so I am just bearing this sum of the trend in the line. So what this is, suppose this was the line, and I suppose here is one of the observed value that I have called that the yi. Out of this yi, look at here, this is the yi hat. This is the y hat. You have estimated here from here to here, this was the value, and you estimated from y hat to here. And I would like to see where is the y bar now. This is the position of y bar. If I just connect these lines to the vertical axis, there will be no change, and I will be writing the same name, and this is yi hat, and this is the y value, yi value. This is y, I can call it that this is the yi value. Similarly, just putting there. Now if you see from here, I am just from here to here, this is called yi minus y bar. This is the total variation, and this is called the total sum of square. If I take the square of yi minus y bar square, it becomes total sum of square. So this is yi minus y bar. Look at here again, this was the y value, and this is the mean of the, this is the population mean. So from yi to y bar, the difference is yi minus y bar. So this is total variation in yi. Now we try to capture where is the residual sum of square, and where is the explained portion. Look at here, if you see from here to here, this is yi hat minus y bar, and this is explained portion, explained sum of square, and this is due to regression. As you run the regression, due to regression. And now you can see if we bifurcate it, it comes up to here. Here is some portion. That is yi minus yi hat. And you immediately guess that this is equal to the residual term, that is the ui hat. So this is unexplained. You can say that all this, that below this line, this is the residual sum of square. So I am just, it means I am repeating this, I am just taking the same story on the vertical vertical axis. So I would like to write here, similarly come here from this yi to this y bar. This is now the total variation, and it is yi minus y bar. And if I come here from this yi hat, if out of this one is explained by regression, that is yi hat minus y bar. And out of this portion of this is total variation. This is, you can say that this is yi minus yi hat, and it is unexplained, it is equal to ui. So this is the TSS is equal to ESS, explained sum of square, plus RSS, residual sum of square. So this was the story. This is the whole regression that we always talked about this, that what is this? Our regression model has explained the proportion that is equal to yi hat minus y bar. This is the explained proportion, and R square will be capturing this value. And definitely we know the combination of the explained and this is explained, this is residual or unexplained. So explained or plus unexplained, it is equal to TSS, that is from here, this is whole one, and this is the yi hat minus y bar. So this is the, you can so the, say the logic behind the regression. So this was the different sum of square. Now you should know some of the formulas. These are very simple formulas, and you may be given some of the values and you may be asked to find the values of R square. And now you know that what is R square? It is coefficient of determination, and the other and the good name and the well-known name for this is that it is a measure of goodness of fit. So this is, there are different formulas. Definitely look at here. This is the RSS. It is the explained sum of square divided by total sum of square. Here yi hat and yi are in small alphabets, so these are the deviation from their mean. So this will be simply summation yi capital yi hat minus y bar square, and simply this one will be total sum of square summation yi minus y bar square. So if you go further, this is another formula, this is other, I need not to explain this, so you should aware of all these formulas. How to find that OLS are unbiased? What is the unbiasedness of the variable? You know what is the unbiasedness of variable? Of the estimate. So what this says, the in practice, if we make the practice, mathematically we can simply say that this is that the expected value of yi as beta 1 hat should be equal to true beta. This is mathematically, but in reality, how we come to know that this is the unbiased? So for this we will be doing the Monte-Carlo experiment. Monte-Carlo, there was Gauss-Markov theorem, and this is the Monte-Carlo experiment. This is a practical thing, and I will suggest you that when you learn the E-views, you should come with this, that you apply this on the software that is the E-views. So what this way, this is a 9-step procedure. First, in practice, how does one know that the below property holds? Below property is, this is the unbiased. So what is, the answer is the Monte-Carlo. I think that there may be a mislink between my discussion previously. I would like to give you that why Monte-Carlo experiment. Monte-Carlo experiments practically help us to find by doing practical exercise that our parameter is unbiased. Mathematically very simple to write, and there is derivation for this that proves that the expected value of the estimate is equal to the true parameter. But in Monte-Carlo experiment, we will be doing some of the things, and I will again suggesting you that whenever you learn the E-views or any of the statistic, even you can statistical software, even you can do it on the Excel, but it will help you a lot. At one side, it will enable you to work on the statistical software. On the other hand, it will make your confidence more concrete that what is the concept of biasness, and when we take many values of the same estimate from different sample, ultimately their average is equal to the true parameter. So how the Monte-Carlo experiment start? Suppose the values of the parameter are as follows. This is total supposition. You should not confine yourself up to these values. Do not think that these are the Quranic values and you can't change and this. You can change this I have just to come up with some of the values, and I will explain that what is this. The first step is assume values, and I suppose that beta 1 hat is equal to, I will go to the that it is beta 1 hat is equal to 60 and beta 2. I have just went the previous slide because there is symmetry in my discussion. Beta 1 hat is equal to 60 and beta 2 hat is equal to 0.75. If I want to draw it roughly on the diagram, you will immediately come that on diagram I am saving the space here because I have to do other things. This is, you can say, the y, this is x. Now this is just position. This is now it comes y is equal, the model becomes y is equal to 60 plus 0.75 x. So this is, what is this? This is the intercept. Beta 1 is here 60, and this is, if you see the slope, this is, what is this? Change in y with respect to change in x is, and it is dy over dx. We have supposed that this is 0.75. This was the first step. Again, I will say that you can assume many values, and I will be very happy and I will be very convincing that you take on your own values. I will be explaining all the steps, and then I will be setting it, the ball, I will be kicking the ball in your courts that you have come with some concrete exercise that you change the values of these parameters. This was the first step. In the second step, we choose the sample size, say n. It is again supposition. You can change the value of n. So here I assume, this was our first assumption, here I assume that the n number of observation in our sample is 25. So what this means, that there will be 25 pairs of x and y values. X values will be 25 and the y values will be 25. I am just going to draw some of the columns and I will show that what is there in reality. Now there is the third one. We fix the values of x for each observation. In all, we have 25 x values. Look at this. In the beginning, we suppose that our model is this. This is our population model. I would like to write it there that we started that this is yi is equal to beta 1 plus beta 2 xi plus ui. Because we have not by now estimated beta 1 and beta 2, we have supposed. Supposition is much different from the estimation. So I am calling it that yi is equal to, so what I said, now I have the values of beta 1. We have supposed it is equal to 60. We have the value of beta 2, it is equal to 0.75. So what I take, I suppose I take that there are 25 x values. This is the x and values are from 1 to 25. These are the fixed values. This was our third step. So this was, suppose the value of the x's. You look at there. We fix the values of x for each observation. In all, we will have 25 x values. You can see that here we have 25 values. Now what is the fourth one? Suppose we got to a random number table. It is very interesting. If you go into the Excel, you give the command rand, R-A-N-D, rand, it will generate random numbers. And you know what are the random number? Every time when you will be giving this command random number, it will be generating different random numbers. So you can generate random numbers from any of the statistical package. For example, the eViews, this one, the Excel, and many others. So what we are using, and when you will generate these numbers, 25 values, and call them UI. Look at your model. You have beta 1 at this problem is solved. This problem is solved. These have the values. You have the values of xi. So this is the problem is solved, and now you have generated randomly 25 values and you call them that these are the UI. So I can say that now you have the values of UI and from 1 to 25. Now the problem is solved. Now what you have to do, you can generate the values of YI, because look at here, you have UI values, 25 values, XI values, beta 2, beta 1 and YI. Just substitute these values. For example, I give that I want that YI is equal to 60 plus 0.7, and I assume X1 is 75, and I assume X plus UI, I assume that this is a random number and it is 2. So what this will be, so I will come up with the values of Y. This will be 60 plus 75 plus 2. So this will become 62 and it will become 137. So value of the Y will be 137. There may be in the change, maybe in the error in the just summation, and I think that there is no error. So what was this step? This was our fourth step. Up to fourth step, I would like to repeat the discussion again. What we are going to do, we are going to see whether our estimates are unbiased. Unbiased means if we take the expected value of our estimates, it should be equal to the true value of the parameter of the population. Now we have taken, suppose, the true value, and we can compare it at later stage. What is the fifth step? Since we know beta 1, beta 2, Xi and Ui, we find the Yi values. Look at here, this is only the Y1 value. Y1 value. So now we have the values of 25 values of Yi, 25 value of Xi, 25 values randomly generated by Ui, and there are fixed values of parameters that are beta, that is 60 for beta 1 hat and 0.7 for beta 2 hat. Now using the 25 Yi values thus generated, we regress these on the 25 axis. Very good, interesting here. Now look at here. This is the Y. अब आपके पास Y भी 25 values आ गई. From 1 to, the first one was 137, I assume, and I assume further that you have 25 values of Y. Now you have 25 value of X. We suppose these values from, this is X. Now you have gotten the values of the Y by a specific procedure. What was the procedure? You assume the values of beta 1, beta 2, Xi, and you generated 25 values of Ui. So now if you regress now you adopt the regression analysis and you regress here that Y is equal to beta 1 plus beta 2 X. And now definitely you will come that Yi hat is equal to beta 1 hat plus beta 2 hat X. So this is your estimated model. Now come here, what is the sixth step? Now using the 25 Y values thus generated, we regress these on the 25 X values chosen in step 3, obtaining beta 1 hat and beta 2 hat the least square values. Now we have the values of beta 1 hat and beta 2 hat. ये रिग्रेशन से हमारे पास वैल्यू आई. पहले वाली वैल्यूज से इसको जो है वो आप कंफ्यूज ना करें, वो पॉपुलेशन की वैल्यूज हैं, आपने सपोज कर लिए. नाउ हियर व्हाट यू हैव, नाउ यू हैव रिग्रेस्ड, यू हैव डन द रिग्रेशन एनालिसिस and you have come with the values of beta 1 hat and beta 2 hat. The seventh is, I am not supposing that what are the values. The seventh step in this is, suppose we repeat this experiment 99 times. This is not a fixation. I can say that we repeat this 90, 100 times. I says that we repeat this experiment by 9 million times. So I am just keeping the thing simple so that you can do this. You will be immediately doing this 99 on your software. 99 times, it doesn't take much time. You will be doing it very easily. So when you will do it 99 times, each time using the same beta 1 and beta 2 head. जो आपने सपोज किए थे, बीटा 1 आपने सपोज किया था कि ये 60 है and beta 2 is equal to 0.75. So you will repeat this process. Similarly, you will be generating the residual random number 25 values. X की वैल्यूज भी वही रहेंगी, बीटा 1 की वैल्यू भी वही रहेगी, बीटा 2 की भी, लेकिन every time you will be making random number of 25 residual values. So if I come here, what will be happening every time? Look at here, ये value will remain constant, this value will also remain constant, आपने suppose की हुई है, and definitely only this and xi will be also fixed. Only every time this number will be changing, that you are generating from the random number series, and these are the statistical package and they can generate for this. So now look at this. I will again write here that yi is equal to beta 1 plus beta 2 xi plus ui. This proportion will remain fixed, but this is random. It means every time you are getting some different values of yi, because I is depending on two proportion, one is fixed, the other is random, and every time when you will be generating 25 random random values and you will say that these are the ui values, you will get the different values of yi. हर दफ़ा आपके पास yi की वैल्यूज़ इस सिमिलर प्रोसेस से जो है वो डिफरेंट आ जाएंगी. बेशक आप जो है वो इसको जो है you suppose keep on supposing 60, 0.75 and fixing the values of x. So now after this I will be going and you will repeat this 99 times. What will happen? You will get 99 and 1, the previous one, you will get 100 values of beta 1 hat and beta 2 hat. Look at here. Every time now you will be regressing yi is a function of x. You will be regressing yi on x. और जब आप इसको estimate करेंगे beta 1 hat and beta 2 hat, these will become different values. Every time you will come up with the different value of this pair beta 1 hat and the beta 2 hat. What will happen next? Of course, the UI values will vary from experiment to experiment. इसीलिए ये YI change हो रहा है, और YI change हो रहा है तो आप regress कर रहे हैं YI और XI को. तो आपके जो regression में आप estimators हैं beta 1 hat and beta 2 hat, they are changing over time. Therefore, in all we have 100 experiments, thus generating 100 values each of beta 1 and beta 2. In this process, at the end you have 100 values of beta 1 hat and you have 100 values of beta 2 hat, and this was the step number 7. Now what you have to do? We take the averages of these 100 estimates and call them beta 1 hat bar and beta 2 bar. What we do here, for example, we have the 100 values and we take that summation beta 1 hat over n, that is the 100 here, and similarly summation beta 2 hat, 100 values हैं इनकी, over n, this is 100. And what we will call that this is beta 1 hat bar, average value, and similarly I will call it that is beta 2 hat bar. This is its value. So what this means, now the story is coming to end in Monte-Carlo experiment. What this means, if these averages, अब आपने 100 जो आपके beta 1 hat थे और 100 beta 2 hat थे, जब उनकी एवरेज ली, तो if the average of this beta 1 hat bar is equal to 60. इसको 60 के बराबर होना चाहिए, and I think you should be guessing that beta 2 hat bar should be equal to this one. You can say that this should be equal to 0.751. If the averages of values are about the same as the true value of beta 1 की आपने true value क्या suppose की थी? You suppose that it is equal to 60 and this is equal to 0.75. Assumed in step 1, this Monte-Carlo experiment, this is called the Monte-Carlo experiment, and it established that the least square estimators are indeed unbiased. अगर तो ये उसके बराबर है, and I am sure, and I am dead sure that the averages of these parameter will be definitely very, very close towards the true parameter that are 60 and 0.75. Why these could not be exactly equal to? Because you will be rounding off the numbers when there will be decimal, and sometimes you will be rounding up to 1 decimal, 2 decimal, and there will be only very, very small difference. And as the number of your experiment will go high and high, for example, your number of this experiment goes to 200, then we will see that you are achieving the more and more precision of the parameters, and your parameters will be unbiased. So what is, in 2 sentences, what is the Monte-Carlo experiment? Very interesting, very important, and it will increase your confidence on the unbiasedness, on the blueness of the parameters. So what you will be starting here, only how to start this I will tell it you in the summary of as I am going to tell this. I think now it is time to wind up the lecture, and I will be telling you the story. I will be telling you the summary that we have just covered in one of the previous hour. So from where we started, if you remember, we started from the Gauss-Markov theorem. Very important theorem because it is about the properties of the least square estimates. Every time I am now feeling a bit, you can say, uncomfortable, that I will repeat again and again beta 1 hat and beta 2 hat. Now you should come up with this, that you understand what is the estimates and what are the parameters. So we explained that the Gauss-Markov theorem helped us to explain that if the fundamental assumption of the classical linear regression model are fulfilled, then the least square estimate have the 3 basic characteristics, and these are called the below. What are these characteristics? First is that these are the linear function of the, you can say, the random variable y. The second is that they are unbiased, that if we take the expected value of all the betas we estimate from our different sample, their expectation should be equal to the true parameter, that is the beta 2 hat, and we also proved this by the Monte-Carlo experiment. The third was that if it has the minimum variance, for example, you estimate one beta from the OLS and other from maximum likelihood, the minimum variance will be with the OLS. So the estimate with the minimum variance, it is also called the efficient estimator. I showed you the diagram, and I just suppose based on some of the assumption, I showed the sample distribution of the parameters, and when I suppose that beta 2 hat has been estimated from the ordinary least square method, and the beta 2 star has been estimated from maximum likelihood. So when I draw the distribution, you came to know that the beta 2 stars distribution that was estimated from someone other estimated the parameter, it was more spread. It means its variation was higher. The variance of this beta 2 star was greater than beta 2, and we want the minimum variance, because if we have the minimum variance, go to your concept of the precision of the estimate, you will come to know that the minimum variance, the minimum standard error, and the more precision. After this, we explained the coefficient of determination at the end of regression analysis. We are concerned with that how much our the model best fit to the data. Everyone may claim that his model or her model is very good according to data, but there is some numerical value that is called the coefficient of determination, and in bivariate regression model we show it by small r square, and in the multivariate regression model we will be showing it by the capital R square. It is just a measure of goodness of the fit. It explains, it gives us a numerical value that how much variation is y, variation in the dependent variable is explained by the regressors, that is the x's. So if there is 80%, we say the model is very good. But keep in mind that always the higher R square value is not welcomed with open heart, because in time series data you should come up with a higher value of the R square, but in the cross-sectional and the panel data it is not necessarily that every time you get the higher value, and you should not be worried about this. Even in cross-sectional and panel data, even your R square is less than 40%, it is acceptable. Then we talked about the Monte-Carlo experiment, the very interesting, and at the end of this you can say the summary, I will suggest you that you should go for this, and you should do it on some of the statistical package. Now you will be worried about this, that how you learn the statistical package. In my present, need not to worry, I will be there to help you, and you will be thinking that why I am talking about every time about the eViews. eViews is user friendly, it is not the better than the other statistical package, but why I have chosen this is the more user friendly, and in one of the lecture I will explaining how to run the eViews, and when I teach you the eViews, I expect and hope for your expertiseness that you do the Monte-Carlo experiment and you prove that the estimates are unbiased. It is a 9-step procedure. I will be just giving you a glimpse of this, that your story starts in Monte-Carlo experiment. Your story starts from supposing 3 things: the fixed values of x. It is according to your number of observation. If you want to put the sample n is equal to 100, you would have to fix the x values of 100, and you should suppose beta 1 and beta 2. Now these will be, we will supposing that these are the population values of the beta 1 and beta 2. You can say that these are the parameters. From this, you will be only changing one thing, that is the UI. You will go to the Excel, you will write the random, and it will generate to according to your desire. If I suppose n is equal to 100, it will generate 100 random numbers, and you will call them UI. Now keep in your mind that on the right hand side everything is with U, and substituting just values you will come up with the yi values. Now there is a data, there are 100 values of yi and there are 100 values of xi. Now use the techniques of your regression. Now when you will regress, you will come up in the first regression experiment, you will come up the first value of the beta 1 hat and the first value of the beta 2 hat. Repeat this experiment many times. I will suppose even 500 times. Do not get afraid that how you will do this by 500 times. Statistical packages can do it in a very short span of time. So what you will be doing, every time all the things will remain fixed, but the UI is changing, that is the random number. Every time you are generating new series of random number and calling them the UI, and when you were calling them the UIs, you will getting the different values of yi. Xi will remain the same, yi will be changing every time, and when you will regress this different values, 100 times you will come up with the values of beta 1 hat, 100 values of beta 1 hat, and 100 values of beta 2 hat. When you will come with these values, now take the average of beta 1 hat and beta 2 hat and just just compare it to your first step where you suppose the population parameters values beta 1 and beta 2. If the average of these 100 values beta 1 hat and beta 2 hat comes equal to your true parameter that you supposed in the first step, then your parameters are unbiased. And this is the story behind the Monte Carlo experiment. I am sure I was a bit quick in the summary, but I think you have got the idea of what we studied today. For your attention, I am very happy and thankful to you for this. So goodbye and Allah Hafiz.